just start recording and we should be good. Alright, hello guys, girls, everything in between. Welcome to 3CL Midterm 1 review session. I hope you guys are doing, if not fine, then tolerably alright. But yeah, let's just get started. So what I have in plan today is just I've got 5 problems that I chose. 4 of them are from the recommended, the problems, and one of them is from tutorial, which I thought will cover most of the concepts that we need for this. Anyways, so first question you have here is from module 2 set 1. So feel free to follow along. I'm watching the chat. You know the drill. You can always just like tell me if I'm missing something, or if there's any questions. I probably can't check the chat and the questions at the same time because I'm writing on the screen, but once I have the once I finish a question, I'll go back and check the chat, if that's cool with everyone. With that said, let's just get started on this one. So I'm just getting my tablet out. 1 second, guys. Sorry, I'm used to pen and paper. Oh, am I coming through clearly? Can everyone see the screen? Just want to make sure. If not, I can fix something up. Okay, thank you. Right. So first question is a problem, mass spring damper system problem. You guys have probably seen this multiple times, but I didn't want to do the one you did in the tutorial because that's very, like long-winded and stuff, so I just will do this one. So whenever you see a system like this, the goal is to do a, free body diagram of each part. So we have a few things given. We need to find the differential equation. So we can start with the free body diagram for each mass. Let's start with M1. So I'm going to draw out the mass here, M1, and we can, when you see something that says a vibration observed, it's usually there's no gravity involved. So this is just to observe vibrations itself. Anyways, so we will have the force coming in as marked, F of t. We have the spring is going to resist the force, so I'm assuming that the force is enough to overcome the spring, and that's going to be K1 and Fk1, I guess. And you'll have the force of the damper. Now a damper will always act to oppose the current direction of motion. So if the force is pointing downwards, that means that the object is accelerating downwards, so the damper is going to try and slow that down. So we'll see a damper force, we can call it Fd, let's say. And then you'll have the other spring, which is below it. So that's the force of the spring below. So that's going to be resistive in this direction. K12, I think that is the syntax we have here. So now we can solve for a few things. So remember that all these forces are going to vary with time. So we have to write individual equations for all of them. So let's write down the equation for a few of these things. So let's say the force of the spring, like I've said, is Fk1. So I'm going to say probably easier if I just call it, sorry, let me just spin this. Probably easier if I call this just K1 and K12 and D, let's say. So K1 of t is equal to K1, and remember that it's proportional to the extension, so x, and the extension is the difference between the current position and the rest length. So on the diagram we have the current position as y1 of t, and the rest length is going to be, well, we can call it whatever, let's just call it L1. So K1 of t becomes K1 times y1 of t minus L1. So far so good. So this is going to be equation 1. We'll use this one. Now we need to find the force that the damper exerts, the D. So I can say D of t is Actually, let me use a capital D. Yep, so DFT is going to be the damping coefficient times the, well, a damper acts upon velocity like I mentioned earlier, so this will act upon dy1 of t over dt. The reason I'm not putting this as negative dy of 1 dy by dt is because the direction of force I've marked in my free body diagram is already upwards, so that accounts for the negativity. But if you decide to point the direction of force downwards, then this is going to turn out to be negative relative to the motion. Moving on. Then we have spring 1, 2, the force of spring 1, 2. So I'm going to say over here, K12 is equal to, oh sorry, this is going to be equation 2. And K12 is going to be, this is a bit tricky, so I'll try and explain it like in detail. So this is going to be proportional to, of course, the actual spring constant itself, K12 times x of the spring 2, and the spring 2's extension is decided by a few things. So the position of the block below y2 of t is going to decide how much it gets stretched by, and the position of the block above is going to see how much it gets compressed. So we know that overall it's going to be compressed since I drew the force pointing upwards. That's the assumption I'm making, that the force is enough to override, is enough to cause this to compress against the force. So I can say that the extension of the spring is equal to the rest length of this spring, so that's L2, minus the distance that this block travels over here, that is y2, and plus, because this is going to be going inwards this way, the distance that this block travels here, and then finally is the distance between them, so that's going to be h. As I mentioned earlier, everyone on the same page so far, I hope. Let me just quickly check the sorry, wouldn't K12 be pointing downwards? Yeah, like I mentioned, the K12 it would be pointing downwards if it had a if the spring was pulling against M1. But in this context, when you apply a force F to the block M1, I assume that the block M2 is going to have the force transmitted to it through the spring, and to have the force transmitted to it through the spring, it needs to go through the spring K12, which means the K12 needs to compress. Oh, sorry, L2 is the rest length of the spring currently, so that's this distance here. 1 second. If K12 goes up into M1, then it should be going down into M2. Yeah. If a spring is going up into M1, then it'll be going down into M2. Yeah. But I'm drawing the free body diagram for M1 right now, that's why it's pointing upwards. Okay. L2, yeah, I already addressed. Okay, so these two questions. Okay, let me try to extend. Let me try to like actually write this a bit more elaborately, I guess. So the rest length of the spring x2, the extension of the spring x2 is going to always be the difference between the rest length and its current position. So how do you know the, well, the rest length I can assume is L2, and the current, so the difference between this and the current position. So how do we determine the current position? Well, we know the current position at the bottom is y2 of t. So I'm going to put y2 of t here, and it is going to be, the current position is, if we just consider the spring extending, it would just be y2 of t, but again the spring is being compressed by m1, so there's going to be a factor of y1 of t against this, so it's going to be minus y1 of t. Is everyone following so far? Sorry if I'm like doing this in a strange way or something like that, that's on me. Yeah, okay, so, and The h is the distance over here, because remember that I'm looking at the point over here, but there's also the measurement of y1 is being done from the top of the block. So at the bottom of the block we're considering the spring being compressed and so on, so it's going to be a additional on top of this another h of distance, right? So this plus h. Does this make sense now? Because normally if this was y1 of t, then this would be fine. But since y1 of t is above, if we're being particular, the coordinate system which starts here at 0, this distance is y1, this distance is h, therefore this whole distance is y1 plus h. So this which starts at y1 plus h, that's why I'm using that as the starting point. So that's why I write y1 plus h here. And then when you expand this bracket out, you get what's written on the bottom. So, okay, all good so far. Right, so this is the hard part over with. Now we just need to assemble the differential equation. So we can say that the net force is the sum of all the forces. So we can say the net force, usually we consider the resultant as R. So R1 of t is equal to the sum of all these forces. So that's going to be, well, let's call this one number, oh sorry, I didn't actually write this down fully. K12 of t is equal to K12 times L2 minus Y2 of t plus Y1 of t plus H, equation 3. So now this is going to be 1 plus 2, sorry, not 1 plus 2, correction, just rewrite that. So the resultant force is going to actually be F of t plus the other force that's in the same direction as F of t, which is, oh sorry, there are no forces in the direction of F of t, so I'm just going to put minus here, minus 1, minus 2, minus 3, and this will give you the equation R1 of t is equal to, over here I will put down F of t, and then I'll put down the equation 1, K1 y1 of t minus L1 minus the equation 2, and that is the damper, which is minus b dy over dt, and then minus K12, this whole expression over here, L2 minus y2 of t plus y1 of t plus h. Okay, so this is the this is mostly the equation. We don't have the entire differential equation yet. We need to get this in terms of quantities that we know, and the main quantity we haven't considered yet is mass. Thankfully there is a relation between mass and R1 of t, which is the net force. The relation is Newton's second law, which is, as we all know, oh, sorry, I actually just need to move this down a bit, 1 second. Sorry, spoilers guys. Yeah, so this, from here we can deduce R1 of t is equal to mass times acceleration d squared y1 of t by dt, which means this whole expression is equal to this, and if you simplify it a little bit, you can put all the differential terms on one side, you get this expression. Sorry, I should put m1 here, m1 d squared y1 of t divided by dt. This is the first term. Then the second term, this will move to the left, and then I'm going to get plus, oh sorry, plus b times dy over dt, and then every other term is not a differential term, it's all constants. So I'm going to group the terms k1 and k2 together. So that's going to be this term and this term. I'm going to group together since they both have a y1 term. I'm going to group them together, and I'm going to get k1 plus k12 times y1 of t. And then on the other side, we can have all the non-y terms. So all of this becomes equal to, sorry, I'm still getting used to OneNote, guys. This is my bad. I'm genuinely a boomer at this stuff. And this is equal to the force itself, F. I'm going to put it in terms of T, plus K12 times Y2 of T. I'm just expanding out the brackets. And then plus the rest lengths, the terms of the rest lengths, is going to be K1 L1 minus K12 L2 minus K12 H. And this is the first differential equation you can say, essentially. Put this guy in a big box. That's the first differential equation. Just gonna check in. Any other questions that I've missed or something? Yeah, sorry if I'm a bit like unclear. I'm just solving this based on the notes. When I solved this, I'm following those notes, and I wrote it pretty hurriedly, so I'm just trying to like elaborate on it a bit more. But yeah, is there anything else someone would like me to elaborate? Oh, really? Thank you. Isn't that cool? I will keep that in mind. Let me try that up. Insert space here. Whoa, you've blown my mind. Thank you. That's the real MVP of the review session, guys. I'm going to be playing with this all day now. Hello, Tosti. Thank you for paying your respects. I thought you were deceased by now. I should be the one paying your respects. Anyways, moving back, we have... So this is, again, just half the question. We still have the second mass. So I'm going to draw free body diagram for mass M2. Let's just... Right here. Mass M2. Block M2. Again, there's only one force acting upon this, which is the spring, and as Eumann very efficiently pointed out, the force is equal and opposite. So this is just going to be F12, or sorry, I think we call it K12, right? Let's just use that. K12, and this is going to be the force applied upon this particular thing. I don't know who Mahmoud is, but I'm going to assume that's a compliment. Okay, so there's only one force acting upon this. Let's solve for that force. So we know this force already. K12 of T is equal to K12 times L2 minus Y2 of T plus Y1 of T plus H. Do you guys say H or do you say H? I'm not sure what the correct pronunciation is. And we know that the displacement of this is going to be depending upon only this, the resultant force of this is going to be dependent only on this force. So we can say R2 of T is equal to K12 of T. And then we can also say that R2 of T is equal to M2 times dy2 of T, sorry, d squared y2 of T divided by dt squared. It's not technically squared, but hey, we're engineers, who cares? Why is K12 in the opposite direction? Because a spring will always apply forces in opposite directions. So if it's applying a force upwards on block M1, it should be applying a force downward on block M2. Right, simplifying this, pretty simple. You get the equation for this turns out to be, when you combine all the terms, m2 d squared y2 of t by, sorry, dt squared. This is a y, not a g, I'm sorry. and oh sorry, I forgot that there's a y2 term in this. We're not dealing with y1 anymore. So this goes to the left, and then we get plus k12 y2 of t. This is equal to k12 y1 of t plus, I'm just expanding this out in my head, k12 L2 minus, no sorry, it's plus k12 H. And this is the second differential equation. So when you combine the two differential equations, you'll get one. You get these are called coupled DEs, and that means that, see, this that means that the equation for y2 has y1 terms in it, and similarly the equation for y1 has y2 terms in it. So they're both interrelated, which makes sense. They're stuck together by a spring. So any motion done to one will change the motion to the other. Okay, any questions on this? Never mind, it's just cat memes in chat. The FT in the RHS is just R1 of T, yep. No, it's cool, keep the cat memes coming. I just need to lock in. Based. Okay, that's this question done. Okay, next question I have is from module 2 set 2. I just took this question because it talked about a control system that was fairly easy to solve, and honestly, yeah, I'm not being paid for this, so why bother? Anyways, so as it says, we've got an open loop control system, so there's no feedback. This is a module 2 question. And the plant process transfer function is given to you. We need to find the value of k such that y of t equals 1 when t approaches infinity for a unit step input, and we assume 0 ICs. When they say assume 0 ICs, just this is usually the default. I don't think there are any questions which don't have 0 ICs, because in a control system it's usually stateless, and it should be linearized and time invariant and all that nonsense. But yep, let me just open this up. So yep, step 1, as you guys know, with any, if you're given these two boxes, make a transfer function. Yep, basically, as Oyman said it, if you see 0 initial conditions, make a transfer function. Transfer function of this is going to be the ratio, as you know, of the input of the output to the input. So we can look at the block diagram. Always look inwards, like so. And you can see that to get YFS, we go through the process, the controller, and so on. So you just have to multiply them together to get RFS. So YFS is equal to the process 1 by s plus 50 times the controller k times the input RFS. This is a property of Laplace systems, and so we can say TFS is equal to k over s plus 50. This is equation 1. So you can easily look at this and know that there is a pole at minus 50. If you drew this out, this would be a very, very, very stable system that would tend towards stability almost instantaneously, because it has a pole at like negative 50, which is very good. Okay, it's just more cats. So with this given, the goal is to find the value of k such that y of t is equal to 1. So we know the input is going to be a unit step, which means that the input in Laplace domain is going to be 1 over s. I think you guys already know this. Then we just put this into this equation, and then we get the result is going to be y of s is equal to k times s over s plus 50, and this is the output for a step input. Now we need to find y of t, so we take the partial fraction. This you can just do by inspection, honestly. So we say this is going to be a1 over s plus a2 over s plus 50. I assume you guys know how to do partial fractions, so I'll just skip past this. And the outputs to the partial fractions are going to be a1 is equal to k by 50, and the output a2 is equal to minus k by 50. If you want, you can plug these back in and make sure, and then you will get the result as if you write this down in the Laplace. If you write this down in y of s, we replace with partial fractions. So I take out k by 50 common, and then we have 1 over s minus 1 over s plus 50. You can then convert this to time domain using the inverse Laplace transform. I'm going to insert more space. Thank you again, once again, that kind soul who told me how I could insert more space. It's genuinely so cool. Right, so you guys know how to do an inverse Laplace. If not, it's in the useful information. So you guys can just apply those Laplace transform pairs, LT pairs, and you will end up with y of t is equal to, we take the k by 50 common, we take the k by 50 out, 1 by s's transform is going to be u of t, horrible university, and s plus 50 is going to be u of t but shifted, so that's going to be e to the minus 50t u of t. And now our goal is to find the point at which we know that we need to find the value of k. So let's figure out what lim t tending to infinity y of t. We need to find this. Now we know that infinity is above 0, so u of t above 0 is going to be 1. So we can simplify this equation to k by 50 times 1 minus e to the minus 50t. And now when you plug in infinity into this equation, you will notice that the time term goes to the exponential decays down to 0, so we're just left with k by 50. And we need to find the value such that this is equal to 1, so k is equal to 50. Except you didn't actually need to do any of this. This is what was written in the notes in the solution, but I did it in a different way. And the easier way to do this is to use what's called the final value theorem. I think you guys already know the final value theorem, which states that when you have a when you have a limit that tends to infinity, you can always replace it with a limit s tending to 0. So lim t going to infinity y of t can be replaced with limit s tending to 0 s y of s. If you want proof of this, it's somewhere in 3dp3, I think, or 2cf3. I'm not even sure which course it is part of now. But yep, we can just simply apply this. We use the y of s that we already have. Instead of doing any partial fractions or anything, we just get s times y of s is k over s by s plus 50. Cancel these. So we're left with lim s tending to 0 k over s plus 50, which is equal to k over 50, and this limit must be equal to 1, so k is equal to 50. So keep a lookout for these kind of questions. When they ask you if it looks like a module 2 question, they probably don't need you to take an inverse Laplace. You can just do this, and you don't need to do anything. Yeah, you don't. Yeah, there we go. Conditions of final value theorem, yes, there are, but most systems that we deal with will always follow these conditions since they're stable, so it doesn't really matter. Okay. Yep, exactly. Oh, even better. SRK already said there's no partial fraction thing. So, nice. I never knew that, so I guess I shouldn't have done this question, but whatever, it's cool. Yep, that's right. Or if there is a RHP pole, it's cancelled out by 0, so it doesn't matter, whatever. Yeah, from the barometer that I've got for this paper, it seems like, old school 2CI4 paper, like ruthlessly hard, but it's easy enough if you actually practice the questions that he gave us. So, yeah. Okay, let me see if I missed any questions. Damn, there is a lot of fucking cats. Man, that spoon cat looks amazing. 10 out of 10. 2CI5. Okay, get out of here, grandpa. Okay, moving on. We're 2 problems down. Hopefully I can wrap this up. Wrap this up. By the end of this. No yapping, no worry. We're engineers. It's gotta be analytical. So yeah, to minimize the yap, we're going to just ignore all of this nonsense that it says here. All it says is steady state effect. They've given TD, they've given K, they've given K, and you can assume R of S 0 has not been adjusted as boring. Show that the rudder can be used to bring the ship deviation back to 0. I'll explain what that means in a bit. Okay. Any questions about the question before I actually start solving the question? Oh shit, my cat woke up, guys. We're in trouble now. Hold on, give me a sec, guys. Okay, I'm back and the cat is now in my lap. Hopefully she doesn't meow too much. Right. Let's see. Oh, sorry. Okay, no questions. Right, let's get started. So again, let's start off with the transfer function of this equation nonsense. Let's see. I'm just trying to find my notes on this. No, found it. Perfect. So I'm going to derive the transfer function from scratch because this has a TD. So just for like once, I will just do it. Normally, you can just use the formula. If you have that somewhere in the formula sheet, the YFS is equal to GCFS GS by 1 plus GCGS, RS, the TD term and the noise term. If you have that, you're good. If you don't have that, it's whatever. Anyways, so let's solve this. We know that we can again start from here, work our way backwards. We have this, we have this, we have this, and we have this. So let's solve all of them. So we know that y of s must be equal to some term t of s into, well, let's go up to, let's actually just break this up. Okay, let's try and break this up. Let's call this let's see, let's call this maybe I of s intermediate, and let's call this is R of s, so that's fine. Let's call this E of s for error, and this is already labeled as GC of s, and this is already labeled as G of s. So let's try and redo this. So I'm going to walk from here up to here just at this point. So I'm going to say that y of s is equal to I of s times G of s, and we can say I of s is equal to, well, it's an adder, so we have the TD of s plus the GC of s, again walking our way backwards from here, times E of s, and then we can say that E of s is equal to R of s minus Y of s So combining all of these, you can get the final transfer equation. Y of s is equal to G of s divided by, no, sorry, I'm not going to skip the steps here actually, let me just do it one by one. So I'm going to replace the first equation, I'm going to replace the second equation with the first equation, and we'll get Y of s is equal to G of s times dd of s plus E of s times GC of s. Sorry. Jesus Christ. 1 second, guys. My cat is pressing every key on the keyboard right now. I apologize. And this results in the intermediate equation, but now we can plug in E into this equation, and we get this equation being Y of s is equal to G of s dd of s plus, sorry, this E of s will subtract to R of s, Y of s. And we also know, actually I'm just going to do the simplification step right now, that in the question it's mentioned that R of s is 0 without any disturbance. So I'm going to put in the R of s to be 0, and then E of s becomes just minus Y of s. So I'm going to replace minus Y of s into here, and then we will get the terms, is very simple, minus GC of s, G of s, Y of s. Are we good so far? Oh, sorry, I don't know why this keeps scrolling up. Y of s, there we go. Okay, let me look if I have any questions in the Discord. Yeah, that's the one. Thank you, whoever pasted that. Yep. So if you write this thing down that Limsa can just send somewhere in the formula sheet, that might help you. I have it written on the formula sheet. I was going to go over it later, but okay, we can just skip past that now. And then I can simplify Y of s is equal to G of s by 1 plus GC of s, G of s times dd of s. There we go. And now this isn't technically a response transfer function. I don't know if you guys have noticed. Oh, okay, that was a mistake. Hold on, let me fix this really quick. I didn't even know that was an option. Hold on. Right, so moving this over. This isn't technically a response function. This isn't Y of s by R of s. This actually is in terms of TD. So what we can get is a transfer function T of s is equal to Y of s over TD of s. So for a certain step disturbance as an input, what do we get as an output is going to be defined by G of s divided by 1 plus G of s times GC of s. If you guys can hear all the keyboard clacking, that's my cat. No, I didn't want to control C because my ego is too large. Anyways, now we can actually replace the values that we already have for G of s, for GC of s into the equation. This should be pretty simple. So expanding this out, I'm just going to write here, replacing given into T s, I will get, simply speaking, Y of s is equal to, the function is given as 75 by, let me just scroll up, I didn't do that correctly. Yeah, 75 by s squared plus 10s plus, okay. S squared plus 10s plus 75, this whole thing divided by, my file looks a lot like my s, that's not really a good sign, is it? divided by 1 plus k times 75 by s squared plus 10s plus 75. There we go. And take this common, you can move this to the top, then this gets cancelled with the denominator. We end up with 7, this times td of s, and this turns out to be 75 by s squared plus 10s plus 75k plus 75 td of s. Everyone on the same page for now, I hope. Okay, sweet. Just gonna pull up Discord again. Okay, no thanks. And we're given that the wind force is a constant, so Td of S is constant, which means the Td of T is a constant, which means that Td of S is going to be the unit step function 1 over S. That should be self-explanatory by now. So then we can apply this into the equation right here. Y of S is equal to 75 divided by S cubed plus 10s squared plus 75ks plus 75s. Great. Now the question asks, will we be, we need to find the steady state effect of a constant wind force. So we have k equals 10, k equals 25. This should be pretty easy to solve. The steady state effect says we need to find the limit as the t goes to infinity y of t. So we can just find the limit as s goes to 0, s times y of s. So we end up with y at infinity is equal to 75 divided by, well, I shouldn't have probably combined the s in, but it's fine. And then when this goes to 0, you end up with 75k plus 1. And now you can plug in 10 and 25 and you'll see the result. It also asks, can you show that the rudder can then be used to bring the ship direction back to 0. So we need to find how much the ship has moved from the like given course first. So just insert a large amount of space right here, and this turns out to be how do I go from y of s to y inf? Yeah, so the question asks, in the question it asks find the steady state effect. So I'm going to say that over here y inf is equal to limit s tending to 0 s y of s. And then if you apply the s will cancel with the s that I just combined into here. That'll cancel out, and then all the s terms go to 0. We're left with just these two terms, and yep, that's going to be 75k plus 1. Right. Okay, cool. Back to the question. This part is a bit more confusing, but I'll try and keep it as like concise as I can because the solution was like super yapping. I just want to keep it short. So again, we already know about the equation for y of s. We know that y of s, we know this equation, we know e of s, and we know I of s. But this time, if I say r not equal to 0, what happens, right? So we can apply the equations and we can get the result of this to be, well, I'll again do it step by step. Y of s is equal to g of s td of s plus, I'll expand e of s to not be negative y of s, I'll make it r of s minus y of s gc of s g of s. Oops. Yep, and so far so good. Now this equation itself is going to expand. We need to get the R of s terms to one side, so I'm going to try and write this down as y of s is equal to g of s td of s plus r of s gc of s g of s minus y of s gc of s g of s. Cool. And now we can get y of s. Again, move the other y term to the other side, and that's going to divide among all the terms. So we're going to end up with g of s, not gc of s, sorry, let me just erase that. Yep, g of s divided by the denominator of the y term, that's this one, 1 plus gc s g of s times td s plus gc s g s divided by 1 plus gc s g s r of s. And again, this, if you compare with the one that's given to us, you already can have a look at if you compare this with the one that we already have in the one that Limp Chicken sent in the chat. That's the one that is used. And again, h of s is 1 and n of s is 0 here. There's no noise in the sensor. Okay. So what we need to find is what happens when the we need to find how much R of s needs to change such that given the current wind disturbance, there should be a some sort of R of s, some value that the rudder should turn so that the ship can come to a a 0 point essentially. So I hope everyone's on the same page here. So basically this just comes down to set TD of s as 1 over s. So we get y of s is equal to gs divided by 1 plus gc of s, g of s 1 over s plus gc of s, g of s by 1 plus gc s, g s r s, and this entire term one second, I'm just gonna go make sure I got all the parts of the question. Okay, yeah, so this is going to go to 0, right? That's essentially what we need. So I need to solve for an RS such that all of these terms, that this entire term goes to 0. Yep, exactly. We need y of t equal to 0, which means y of s also equal to 0. It doesn't really matter. The Laplace transform of 0 is still 0. Basically, it's just asking that if there is a certain desired input that we can put in to make sure that the rudder doesn't go off 0. Okay, so we can do like some basic manipulations here, and you can get g of s. I'm just going to move all of this to the other side. I'm going to move all the R of s terms to the other side. So I'm going to replace the gc of s with k, since it's kind of tedious to write gc of s over and again. So g of s, I expand g of s if I need to, but I have a feeling they're all going to cancel out, so it's fine. 1 plus k g of s 1 over s is equal to minus k g of s divided by 1 plus k g of s r of s. And now the denominators cancel. I'm left with g of s over s is equal to minus k g of s rs rs is equal to, now if I just cancel this out, I'll end up with minus 1 over ks. So yes, there is a rudder input that can make this go to 0. This is the rudder input. So we just proved. So the question said prove that there is a rudder input that can drive the ship to 0. So here it is, there is an input, hence proved. You can write this down in time domain. You know the Laplace transform of this, r of s, transform to r of t, and 1 over s is going to transform to u like the step function. So it's just going to be minus 1 by k times u, and that's the answer. Cool. Yep, this is being recorded. Okay. Right. So a couple more questions. We should be done soon. This is the tutorial 4 from Arthur's section. I'm not in Arthur's section, but his section is clearly better, so you know the drill. Right, so I'm just going to follow his logic here, since I think it's pretty well done. So we need to figure out K such that we have stable system, overdamped system, 2% settling time of less than 4 seconds. So a few conditions that we've been given. You could use a Routh-Horowitz table for this. I will be doing a Routh-Horowitz table question in the next one, but I don't think it's particularly necessary since this is a second order system. Like it's just got making an RH table for this would be overkill essentially. So we can just do it by hand. And we need so we know that the system has 2 poles, one pole at 0, one pole at minus p, so it's a type, this system is a type 1 system since it has a pole at the origin. And we know that p must be greater than 0, so that means that the system is stable because p is greater than 0. But okay, let's just do the formula. Let's just do the formalism first. Let's do the transfer function, right? So we need to find t of s. And to find t of s, again, just walk backwards through the transfer function. I think you guys know how to do this by now. So we end up with y of s is equal to gs times k rs minus k ys, and then we get ys is equal to, well, once you move the y terms to the side, you get you can expand this out to be k g of s. I'm just moving the r of s to the outside, 1 plus k g of s, and here I'll write r of s. Then you can find t of s is equal to k g of s by 1 plus k g of s. And again, this is the same as gc of s, g of s over 1 plus gc of s, g of s, r of s. So you already know this. You can just plug it in if you like, but just showing you that it's doable this way. And we also know g of s, we know the transfer function. We can simplify this. We can plug in g of s is equal to 1 over s plus p, p greater than 0, means t of s turns out to be k over, okay, if I multiply out that and then I move all the denominators are going to cancel out, s times s plus p is going to cancel out in the numerator and in the denominator. So we're going to be left with, if my math is correct, s squared plus ps plus k. There we go. Sorry, brain fart over there. I don't know why I can't simplify fractions, but I'm in third year engineering. And now that we have this given to us, we can now find the conditions that are given. So we need to find out whether the system is stable. So for a stable system, all the poles should be in the left half plane, and so for all the poles to be in the left half plane, we need to have the roots of this equation in the denominator be in the left half plane. So you can solve this using the quadratic formula. and in the denominator you will get this over here. You can solve this out, and the roots will be minus p plus square root p squared minus 4k over 2, and minus p minus square root p square minus 4k over 2. These roots should be greater than 0. So that's the first condition. The second condition is that the, or actually I should probably solve, like finish off this condition first. So I can say that both of these roots must be less than 0. This must be less than 0, this must be less than 0. So let's look at this one. If this is less than 0, then we know that negative p, we know that square root p squared minus 4k must be less than p. Simplify a little bit, you can write this down as, I'm going to take p common in the square root, and I'm going to get p square root 1 minus 4k by p squared is less than p. Cancel out the p's, and then we get k must be, so if I move that over there, oh sorry, did I do that right? Oh yeah, okay, sorry. Yep, so 4k over p squared must be less than, no, sorry, must be greater than 0, not less than 0. Which means that k must be greater than 0. So that is the first condition. And we also need the second condition to be true, which is R2 must be less than 0. So I'm just going to write this one over here. So here we have the same procedure, but if you do this, you just get k must be less than p squared over 4. So we have two conditions, k must be greater than 0, k must be less than p squared over 4. So for stability, k must be within 0, p squared over 4. Perfect. So this is just one part of the condition. This is just for the stability. Shouldn't these roots be negative? Yeah, that's right. Okay. So far so good. Let's try and find the overdamping condition. So overdamped condition has real distinct roots. So that we know. This was covered in like many courses before. You guys know that for any transfer function, if you want it overdamped, we need to have real overdamped roots, no overlap. So remember, there's a difference. There's critically damped, there's underdamped, there is overdamped, and for overdamped we need real distinct roots with no overlap. So that means that we need to look at the discriminant of these roots. That's this guy over here. We need to look at the discriminant, and we need to make sure that the discriminant itself is greater than 0 for real and distinct roots. So we can say that root of p squared minus 4k must be greater than 0, which means that k must be less than p squared by 4. However, this condition is the same as over here, so if we obey the stability condition, we will always have an overdamped system. So that's not a worry. So we have the conditions. What else am I missing? Am I missing anything now, guys? Oh yeah, settling time, right. So we need to find 2% settling of 4 seconds and To find the 2% settling time, we need to find the point at which y of t becomes within 2% of the input r of t. Obviously, this won't like happen instantly, it's overdamped, so let's do that part. So 2% settling time must be less than 4 seconds, so less than equal to 4 seconds. Okay, so what we first need to find is we know that we have a for settling time we can take a step input. R of t is equal to u of t, which means that R of s is equal to 1 over s. You can do this for pretty much anything, but the easiest to do is a step input because the settling time should be taken with a constant input in mind. So yep, let's figure out the step response. So I'm going to put y of s for step input is equal to t of s 1 over s, which is equal to k times s squared plus ps plus k. Right. We need to find the time that it takes for this to go to 98%, but this is in frequency domain, this is in Laplace domain, so we need to convert this to y of t. We need to convert this to the we need to convert this to its time domain equivalent. So I'm going to say y of t is, we don't know, let's try and find that. So first we take partial fractions of y of s. Y of s is equal to well, I can take out the 1 over s. 1 over s minus, and if you know that there is a quadratic in the denominator, you can use this form. I think this is well known so far. Sorry, I think my blue light filter just came back on. One moment. It's annoying. Fixed it. A divided by s minus the first root, b divided by s minus the second root. You can, if you want me to explain this, I'd be happy to explain it to you. But yep, whenever you have a partial fraction of the form of a quadratic, its partial fraction denominators will be its roots, and also you can just, because the two partial fractions are being multiplied together, we can know the second term is going to be subtracted from the first term, so we just put a minus sign of a and b, and we can solve for this s minus r1, s minus r2, and if you try to put this into like the I could do this for you, but honestly we're like already over time, so I don't want to like stretch this out. A turns out to be the poles. I'm going to write this in terms of poles, p2 minus p1, b right, and this p2 and p1 are derived from the original transfer function above. So using all of these terms, we can get the resultant y of s transformed to y of t, sorry, lowercase y of t. Y of t turns out to be, the 1 over s is just 1, assuming that the time is greater than 0, minus the term over here is going to go to a e to the minus b1t minus b e to the minus b2t, and this is the step response in time domain. The reason we need to do this is just to find the this is to find the 2% settling time. So we need to make sure that y of 4, that is this, we need to make sure that, sorry, the time taken t to reach 0.98 times a of input must be less than or equal to 4, which means that time for y of t to be equal to 0.98 must be less than or equal to 4, or since we know that this must be the case, we can also say that y of 4 must be greater than or equal to 0.98. Since if it isn't, then we know that this isn't true. So everyone on the same page here? Lovely. So yep, just plug in these equations and you can solve, like you can just put y of 4, we already know y of t, just put in y of 4 into this, put 4 here, put 4 here, use the values of p that we've derived over here, these are the two poles that we had, derive and then put them here, and then you'll be able to prove that this is true. Okay, any questions on this question? It's pretty lengthy, but it's pretty straightforward. Again, like you said, no partial fractions will come in this paper, but settling time and things like that can be asked. You can always use the approximation for settling time, which is 4 time constants. But yep, that's just an approximation. There's also the lab document which has the settling time that you've already calculated, so you can use that if you like. Okay, last question. No worry, guys. I won't be keeping you guys here longer. So this is the favorite question of everyone, Ruth Hurwitz polynomial shaboing boing being done to this question. So yep, characteristic equation is given to you, s cubed plus s squared plus 9s plus 9. So s cubed plus s squared plus 9s plus 9. And we need to find if the system is stable. So let's build up the Ruth Hurwitz table. Why is there a big floating box on my screen? You know what? It can accompany us along our journey of solving mathematics. So simple enough. I hope you guys know how to construct a Ruth Hurwitz table. If not, just follow along and we'll construct it. So the roots of the system are given here, and the question asks us to simply find the points at which the system is stable. So let's put in the system. So we know that we start over here. I'm just going to label them R3, R2, R1, and R0. As you know that when you have a system of third order, there's going to be 3 plus 1, so 4 rows in the Ruth Hurwitz table. So using the numbers, we take this number and this number, 1, 9, second row, this number and this number, 1, 9, minus, this is going to be B1, and this is going to be a 0, C1, 0. Right, so far so good. This is technically wrong, there is no ending to Ruth Hurwitz table. Okay, let's solve for a few things. Let's solve for, can I write in this? Wow. Damn, it even disappears in real time. Okay. So let's solve for this. Let's try to figure out what B1 is. So B1 is equal to minus 1 over the row above. So that's minus 1 over 1 times the determinant of the entire thing above it. So 1, 9, 1, 9. And this determinant evaluates to 0. Fuck. So this is actually a 0 row. And now we have to do some like calculations to try and like establish the what it actually is supposed to be, because you can't have a 0 row. So let's see. We know that we need a characteristic polynomial. So, or not a characteristic, we need an auxiliary polynomial. Now the auxiliary polynomial is a polynomial which the coefficients are the row above the 0 row. So that's the coefficients over here, and the terms themselves are going to be the same terms we used over here. So let's build the auxiliary polynomial here. A of s is equal to 1s squared plus 9s to the 0, which is 1s squared plus 9. Now, we need to replace the 0 row with the derivative of the auxiliary polynomial, which turns out to be 2s plus 0. So let's put that into row 1. The new table looks something like this. R3, R2, I'm going to write R1 dash and R0. So here we end up with 1, 9, 1, 9. R1 dash in this case is again derived from the auxiliary polynomial. So I'm going to put in the coefficients 2, 0 and C1, 0. Perfect. Now we can actually find C1. So C1 is equal to -1 over the element above it, which is 2, and the determinant above it, which is 1, 9, 2, 0. Multiply this out, you're going to end up with this equal to 9. A quick trick that you can remember with calculating C1 specifically is if you are ever calculating C1, just take this value because this is usually 0. So if this is 0, you know that the answer is going to be that one. Just copy it down. Doesn't really matter. You don't have to do the math. So this now the table now becomes 1, 1, 2, 9. Excellent. No sign changes, which means stable. Except it isn't. As I mentioned earlier, you don't have a 0 row unless you have radially symmetric you have a radially symmetric configuration. So the poles have to be directly opposite each other. And if the poles were in any configuration where one of the poles was over here, there would be a sign change. But since there is no sign change, we can conclude that the poles must be here and here. And that's technically not stable. But let me prove it. We know to find it that Q of s is equal to A of s times B of s. That is to say that the auxiliary polynomial is a factor of the original characteristic equation. So what are the roots of this are going to be shared roots of this. So let's find the roots of A of s. So A of s is equal to s squared plus 9, which means its roots are, well, now we're in trouble, plus minus 3j. This is a complex conjugate pair, and if we have a complex conjugate pair, you guys already know that the system is going to be it's not going to be stable, it's not going to be unstable, it's going to be somewhere in between, it's going to be marginally stable. Therefore, the system is marginally stable. Yeah, oh, I should mention on the j omega axis. If you have a radially symmetric complex conjugate pair, they must be on the j omega axis, otherwise it can't be radially symmetric. So this is marginally stable, and whether you want to call this unstable or stable depends on you, but in this course we consider this a unstable system. So this system isn't actually stable, it is unstable, and yeah, using the Routh-Hurwitz criterion you could determine that this system is marginally stable. It also asks you to find the roots. We already found 2 of the roots, plus minus 3j. So if you want, you can do some polynomial long division of Q of s. So we can say that I'm just going to copy this down. S cubed plus s squared plus 9s plus 9 has factors plus 3j minus 3j, and if you want you can take the factors of this, but it's much easier to just look at it, plug in the values, and you'll notice the last one is -1. So these are the roots we have. So the roots would look something like this: -1 plus 3j minus 3j. Not in the RHP, but it's on the j omega axis, so it's marginally stable. You can call it what you want, but for the purposes of the exam, it's not really. Yeah, regular complex conjugate pairs can lead to underdamped or overdamped systems. It doesn't really like we can even have systems which are unstable if the complex conjugate pair lies on the RHP, both of them. But yeah, that's pretty much all the questions I had for today. If anyone has any other questions, I'd be happy to take them up as well. But yeah, on that, thank you all for coming. You guys can head out whenever you like if you don't have any other questions. And if you want like some tips and tricks on building a cheat sheet, you can check out the pin stuff. You can check out the previous midterms. If you want some more stuff to study, there's always the previous midterms. Um, and there is always these recommended problems. I would say do the recommended problems since they are like really fun to do actually. And yeah, thank you all for coming. Good luck on the exam. Have fun. See you all later. I'll upload the PDF. I'll upload the recording once it gets processed and tossed to a drive or something like that, or a common point. So yeah, have fun. See you all later. Bye bye.